So hello everyone, and welcome back to the channel. Today's topic is really exciting, and it's an introduction to game development using Expo, Reanimated, and React Native Skia. So no physical libraries, no anything like that, just the meat and potatoes of React Native. Actually, off to the side, you've been seeing a game of Brick Breaker being played, and the reason for this is because we're going to do sort of project-based learning today, and I'm going to teach all these fundamentals while building this game of Brick Breaker that you see here. Okay, so before getting into too much of the video, I first want to talk about a few different people who influenced this video and were really important to its creation. The first is Daehyeon, who needs no introduction. They've done a lot of awesome work on Twitter and in the React Native community and have done all kinds of things with gaming. I consulted him in order to learn a little bit about sort of collisions in the early parts of this, and he gave me all sorts of valuable information that helped me along the way. The next name that I have to remember is Martin Heinz, and Martin Heinz has an article on collisions that I will link in the description, and actually I recommend you read it after this. My work today is really based on his article that handles like bounce collisions, and I think you'll find the rest of his stuff with like gravity and that kind of thing really interesting as well. Finally, for the shader that you saw in the Brick Breaker game, that shader is actually not mine. It's from Paul Malin. The shader is like the dots that come to you like it's space or something. But Paul Malin's work is really awesome, and I hope you'll check it out. Please follow him on Twitter. In fact, follow all these guys on Twitter. But with Paul, he also has a shader toy, which is really exciting as well. So I hope you'll have a look into all of these guys. All right, so in this video, we're gonna cover all the basics of game development, such as movement, wall collisions, gestures, object collisions, and finally, we're gonna wave hands a little bit at shaders and just kind of show you how to use them, not necessarily how to make them. Remember, this video is an introduction to game development. It's not like a super comprehensive guide, but if this video does well and people want to learn more about making games, Skia and stuff like that, I can definitely look into it. But I'm gonna have to see how this video performs first before I, commit to anything else. All right, guys. So remember, if you get stuck at any point, the GitHub link is in the description to this project. The starter branch will have the starter project that you can follow along with, or you can go to the main branch, which will have the full solution, and you can look at all that code. Okay, so please like and subscribe, guys, or leave a comment. It means a lot to me when you do that, and let's get into it. Okay, so I want to start off this movement section by talking about our variables and sort of the conceptual parts around what we're doing today. If I don't start with this part, it's not going to make a lot of sense once we get into the code. So let's talk about our variable definitions first, and I think that's going to inform a lot of what we're doing today. So of course, there's x, which is going to be our x position, and y, which is going to be our y position. And these of course apply to like squares, circles, bricks, the paddle, anything in our little game. Next, we're gonna have this variable v, which is gonna be velocity. So the speed at which any object is actually moving. And of course, alongside velocity, you have your vx and your vy. That's a v. And that's of course the velocity of x. And this is your velocity of y. So inside of this, we actually have a couple more things to think about. The next is acceleration. And acceleration is, of course, how fast your object is picking up speed. And within acceleration, we have our ax and ay, which, as you may have guessed, is the acceleration of x and the acceleration of y. So the last important variable here that we have to kind of talk about is delta t. And delta t is the difference in delta between frames. There's also a question here of kind of like, what is a delta, right? And it's not a difficult concept to understand. It comes from calculus, but you don't really need to know any calculus to get the gist of it. So say we have like an X and a Y axis, and we have our line that goes through this, and you have like an X1 and a Y1 and like a Y2 and an X2. Basically, the change here between these points is called the delta. So you can see as time goes on, this can go up or down, and pretty much it's just the change in our speed and acceleration as we move through time and frames. So now that we have our variable definitions, let's talk about how we're going to model movement. And the way we're going to do that is we're going to say that Vx is going to be equal to the acceleration of x multiplied by delta t. We're then going to say Vy is going to be equal to the acceleration of y times delta t. Once we have our velocities recalculated, we're then going to get the x position, and the x position is going to be the velocity of x multiplied by delta t, and the value of the y position is going to be the velocity of y also multiplied by delta t. So the math's not all that complicated. There's just a lot to kind of understand in terms of variable definitions. Okay, let's go in now and try to write some code. Okay, so before we start coding, I first want to introduce our starter project and all the different things we have available here. Of course, I'll have a link to this in the description that you can use, and you can check out the starter branch in order to follow along with me. Otherwise, the main branch will have the completed code. So here in the package.json, I just installed some really basic dependencies like React Native Skia, React Native Reanimated, and gesture handler. I also have this constants file. These are some kind of arbitrary numbers that looked really nice in different places in the app. Because they're arbitrary numbers and they don't really have any math behind them, I just chose to keep this and we'll use it as a guide as we go. Finally, the app.tsx, this is going to be the main file. And at the moment, it really just fills the screen. We're going to add a whole bunch of stuff to this to give our game functionality. Okay, so the next thing we're going to work on here is actually creating the models for the different shapes that we have in our project. To do that, we're going to start by creating a file, types.ts. We're going to import shared value from Reanimated because it's going to become pretty important pretty quickly. And I'm going to create a type called shape variant. And we're going to start just with the circle in the beginning. We're going to add more as we go. So next thing that we're going to do is create an interface called shape interface. And all the other shapes are going to basically extend from this interface. And that way we don't have to like duplicate a whole bunch of the different values that we have in every single one. The values in each of these shape interfaces are based on all of the movement logic that I showed you earlier, or maybe some of the collision logic that I'll show later. But basically, this is a good place to encapsulate all this so we don't have to write this code over and over again. So every shape for sure is going to have an X shared value, and it's also going to have a Y position shared value. Now these have to be shared values because they actually control UI on the screen. They can't just be numbers. Next, we're going to have our acceleration X and our acceleration Y. These can just be numbers because they don't actually control any UI. They're just sort of kept as state in the background. Next, we have our velocity X and our velocity Y, which are also numbers. I'm also going to have a type, which is going to be of type shape variant, which we'll use as we go along. And finally, I'm going to have an ID, which is a number. This probably won't come into play much. It's really just for my own debugging purposes. Okay, so since we're going to work with the circle in a minute, I'm also going to do the circle here. So we're going to export interface, circle interface, and we're going to give it an R, which is going to be a number that represents our radius. We're also going to have a type value, and that type is always going to be circle when you do the circle interface, of course. So now that we have our models all ready, let's work on displaying something on the screen. So in app, what we're going to do is we're going to create our circle object, and that's going to be of type circle interface. And we're going to initialize some of the values. The type is of course circle. ID is going to be 0. The X is going to be a shared value with the value of 0. Y is going to be exactly the same. And then everything else, actually the radius is going to be of the radius constant value. But everything else, including like the acceleration X and Y and all that, it's all going to be 0. Oh, and I forgot. My circle interface has to extend the shape interface. That's why I was seeing some type issues there. Okay. So now that that's ready, what I can do is I can kind of start wiring things up here. So I can make a circle Skia component here. And inside there, I'm going to say my CX is going to be equal to the circle object dot X. Then the CY is going to be equal to the circle object dot Y. The radius is going to be equal to the radius constant, and the color is going to be equal to the ball color constant. So at this point, what we're going to want to do is get these values to initialize to the correct circle values at the beginning of the game. And I'm going to create a method to do this so that we can restart it when the game restarts. I'm going to create another file though to separate our logic from our UI stuff, and I'm going to call this logic.ts. So in this file, I'm going to export a function called createBouncingSample. And this is going to take in a circle object. And it's going to set all the defaults for that. Of course, because we're using Reanimated, we have to mark this as a worklet or the app will crash. But what we're going to do is we're going to set the initial values. So the X value of the circle is going to start at 100. The Y value is going to start at 450. These are arbitrary numbers, by the way. They just kind of look nice. The circle object radius is going to be equal to the radius. And then I'm going to set, again, some arbitrary values. The acceleration X is going to start at 0.5. The acceleration Y is going to start at 1. The velocity X is going to start at 0 because it's just started. You won't have any velocity yet. Same thing with Vy. And that should be everything we need to get started. So back in the app.tsx, what I'm going to do is just after this thing is created, what I'm going to do is I'm going to create, oh, did I not export it? No, I did export it. I'm going to do create bouncing example. And in here, I'm going to pass the circle object. Okay, so the next thing that we want to do is actually write some code that will allow us to make movement in the application. In order to do this, we're going to go in our logic.ts file and we're going to create a function animate. And the animate function is really important because it gets called on every single frame in order to manage the movement of the different parts of our application. And not only the movement, but it will actually resolve collisions in the future. The animate function is going to take in a few different things. First being an array of shapes, which we're going to call objects. It's going to take in the time since previous frame. That's going to come into play later, not now, so you don't got to worry about that just yet. And also the brick count, which is the exact same thing. It's going to come into play later, but you don't got to worry about it just yet. And so what Animate's going to do is it's going to loop through all the different objects that we have. So const O of objects, and we're going to say if the object's type is a circle, what we're going to do is we're going to move forward some amount. So let's create the move function as well, because that's going to be equally as important, obviously, for getting movement to work. And the movement function here is going to take in an object, which is a shape interface. And it's also going to take in our delta, which is how much we want that position to change. Oh, and of course, all these things have to be worklets, because if they're not, we're going to crash the app. So don't forget to add worklet everywhere. And move, I can do O, and I'm just going to do 0.1 for now for the delta. Actually do 1.5, maybe it's a little bit nicer. Anyway, inside move, what we're going to do is we're going to implement that exact same physical logic that we had earlier in the conceptual explanation. So we're going to say that the object's Vx is going to be equal to the object's AX multiplied by the delta. And we're going to say the same thing about the velocity Y. Then after that, we're going to say the X value is going to be equal to the object velocity X times the delta. And we'll do the same thing with Y. One last thing we're going to want to do here is set a max velocity, otherwise these can get really out of hand and crazy. So we're going to say if the object's Vx is greater than the max speed that we defined in the constants, we're just going to set this equal to the max speed. After that, we're going to say if it's less than the negative max speed, we're going to make this equal to the negative max speed. And then we're going to do the exact same thing with y. And we're just going to say Vy is like that. Y, Y, and Y. Okay, so there's one last piece to get movement going. And that last piece is to go into the app.tsx, and we're going to add a reanimated callback called useFrameCallback. And inside of here, we get a really special value called frameInfo. And probably gonna not need that just yet, but I'm gonna add some protections just in case. So if there's no time since previous frame, we're just gonna return. Probably this would never happen, but we just add it there just in case. But otherwise, what we're gonna do is we're gonna have our animate function. We're just gonna put our circle object in here. I'm gonna add the time since previous frame, even though we're not using it just yet. And for our brick count, I'll just do 0, because again, we are not using it just yet. Oh, it has to be a shared value. I'll just make this a number for now so that we can just put a filler in there. And we'll worry about the brick count a little later on. Okay, let's see really quickly if this worked. So back in my bundler, I'll fire up the app. Actually, let me reload it really quick. And as you can see, we get movement. Right now it runs off the screen, which is obviously not what we want, but we're gonna work on collisions to get it to stop running off the screen. Okay, so now that we're done talking about movement, let's talk about collisions. And I'm really only going to talk about wall collisions here, because all the rest of the collisions we do are really just an adaptation of this. And I find that collisions are really easy to understand if you start with how the coordinate system kind of works. So at the top left-hand corner, our x and y are 0 and 0. At the top right-hand corner, it would be width and 0. In the bottom right-hand corner, our maximal value would be width and height. And in the bottom left-hand corner, it would be 0 for the x value, and h for the height. Now, let's say we have a ball, right? The ball's right here, and the ball collides with the wall right here. What do we do, right? First thing that we're going to want to do is take our y value, and we're going to reset this value to the value of the height minus the radius of the circle, so circle radius, times 2. And the next thing we're going to do is pretty easy. We're going to take the acceleration of y and invert it. And we're going to take the velocity of y and we're going to invert it. And so that's going to take our ball, it's going to move it off the wall just a little bit, and it's going to send it going in this direction. So the next question is then, what happens if we collide with the wall, right? Like on the right-hand side here. And basically what happens is something very similar. We reset the x position to be equal to basically the width minus the circle radius times 2. And then we just invert the x velocity, and then we invert the acceleration of x. And that will allow us to basically take our ball and now have it kind of bounce off in this direction. So I'm not going to go through all the different possible ways that this could collide with the wall because we pretty much just follow this pattern through, but this should be enough to get us started and get us into some coding. Okay, so now that we conceptually understand how wall collision resolutions work, let's actually create a method to resolve our wall collisions. So we're going to call this resolve wall collision. And this is going to take in an object, which is a shape interface. And of course, the method has to be a worklet. First thing that we're going to do is we're going to cast this to a circle object because we know that what's going in is going to be a circle object. And in order to guarantee this, we're going to create another loop, which is also through the objects. And we're going to say that if the type of the object is a circle, then we're going to call our resolve wall collision with our object. Okay, so the first thing that we're going to do is we're going to check whether we collided with the right wall. To do that, we're going to say if the circle object dot x value plus the circle object's radius is greater than the width of the screen, then we're going to calculate the new place you have to be. So we're going to say circle object dot x dot value is equal to the width minus the circle object dot radius times 2. After that, just like we did in the earlier conceptual explanation, we're going to reverse the velocity of x and we're also going to reverse the acceleration of x. Okay, so that we can make a little comment too. We can say right wall collision or something like that. So next we're going to have an else if here, and this is going to be for a collision with the bottom wall. And to know if we collided with the bottom wall, we're going to check if the circle object y value plus the circle object's radius is greater than the height. If that's the case, then what we're going to do is we are going to basically take what we did above and we're going to do y value, we're going to take the height, and then we're going to invert y in all of these cases as well. Okay, next we're going to do the left wall collision. And then that's going to be if the circle object dot x dot value minus the circle object radius is greater than 0. We're going to say the circle object dot x value is going to be equal to the circle object radius times 2. The circle object vx and ax are again going to invert, just like they do up here. And then the last one we have to do is a top wall collision. Oops. And that's going to be if the circle object dot y value minus the circle object radius is less than 0. The circle object x value is then going to become basically just the radius. And then, just like earlier, we are going to reverse the velocity and acceleration y. So now that we have this all plugged in, let's run the app and let's see if everything works like we think it should. Okay, and that didn't work, probably because I made a couple errors. And yes, I see some copy pasta errors here. So let me fix those really quick. And now if I start this up again, let's have a look. And let's see if it collides properly. Yep, that's the bottom, left, and the right. Yep, and as we can see, all the different collisions are happening off the wall exactly the way that we'd want them to, which is awesome. Okay, so now that we've done some simple work with wall collisions, which is probably the easiest type of collision to handle, let's now work on gestures. So what we're going to do is we're going to get that paddle actually to be displayed on the user interface. The first thing that we'll need is a model of the paddle so that we can keep track of all its different pieces of state. And we're going to create an interface for this called the paddle interface. And it's also going to extend the shape interface. The unique things that we're going to have in here is that the type is always going to be paddle, and we'll have to add that type up here. After that, it's going to need a height, which is going to be a number, and a width, which is going to be the number. Remember that the x and y are shared values, so everything else can just kind of be stored up as state as just a normal JavaScript value. Okay, so back in the main app file, I'm going to create the paddle. And I'm going to say that this is a paddle interface. And so our type is obviously going to be paddle, just as we already knew. There's only going to be one of these, so I'll just make the ID value 0. The x is going to start at the paddle middle, which is a constant that I made. The paddle middle is just basically the width of the window divided by 2 minus the width of the paddle divided by 2. That's roughly the middle of the screen, or at least where we want to put the paddle on the y-axis. Oh, sorry, on the x-axis. As far as the y-axis goes, I'm going to take the total height and subtract 100. If you remember, the total height is the coordinate that's at the bottom of the screen. So I'm just taking the bottom of the screen and kind of pushing it up a little bit. The AX and AY values and so on and so forth, VX, VY are all going to be 0 because the paddle's not going to bounce off anything or do anything like that. It just kind of stays fixed. So I'm going to give it a height from the constants and a width from the constants. Last thing we're going to do is we're going to wire this up. I'm gonna make it a rounded rect just because rounded rectangles look really cool. And let me quickly check my notes. Okay, so we're gonna say x is rectangle object.x. The y is equal to the rectangle object.y. The width is going to be equal to the width of this object. Height is going to be the same thing. And then we're going to make the color white. And the radius is going to be equal to 8. So if I go into the app now, we should see our paddle. And we do. There's no collisions yet. You see the ball is just passing through. We're going to worry about collisions in a bit, but next let's check into making the gesture. Okay, so in terms of creating the gesture, let's start with the obvious stuff that we always know we have to do. We're going to add the gesture handler root view and give it a nice big size. After that, we're going to add a gesture detector. And this gesture detector is going to need a gesture. So let's really quickly create one. And it's going to be a pan gesture. And I'm just going to plug this in really quick so it stops screaming at me. So the next thing that we're going to do is we're going to say that on change, we want to change the value of the object's x position. And the way we do this is going to be by taking our rectangle object and the x value, making it equal to x. Now this is going to work really weird, and I'm going to show you how to fix it. Actually, there's a few things that are going to work weird, but let's start with this weirdness before we get into the next weirdness. So if I try to move this around now, you'll see that the paddle always jumps to where my mouse is, you know, like the front of it. And that's not really what we want. We want it to kind of be more in the middle, because most people are going to touch the paddle in the middle, not on the far left-hand side. So to get that happening, we basically subtract the x value from the paddle width divided by 2. So halfway down the paddle, basically. And what that allows us to do is now we're going to snap to the middle of the paddle instead of snapping to the far left-hand side, because that was just very uncomfortable and a little bit weird. Okay, so another thing you'll notice is that while I'm moving the paddle, everything speeds up, right? Like that's not what we want, and that's really strange. And let me show you the reason for that. I'm going to quickly log the time since previous frame, and you'll see it's right around 16 milliseconds every single time. But as soon as I move the paddle, things get pretty wild, right? We're getting negative numbers, we're getting small numbers, we're getting higher numbers. Moving the paddle basically causes the useFrame callback to get called a lot more frequently and with various different values. So what we have to do is we have to go into our move function here, and we have to make some changes. And the changes are pretty small. Basically, what we do is in our move function, instead of using 0.15, which is what we want the speed of the game to be, we have to divide that by 16 for 16 milliseconds and multiply by the time since previous frame, and that will smooth things out for us. So let's go back in here and reload. Now if we can move this paddle around as much as we want, and the game doesn't speed up or slow down, it stays at a nice even 16 FPS, which is really awesome. Alright, so the next thing that I want to do is talk about how we get the collision working with the paddle. And the first thing that we do, of course, is pass our rectangle object into the animate function. Okay, so the next thing we need to do is talk about other collisions, right? We talked about collisions with the wall, which is probably the easiest type of collision that you can handle, But there's obviously other ones too, right? Like squares with circles, circles with other circles. And in order to really get that information in depth, I recommend going to this website, jeffreythompson.org, and I'll link this website in the description. But here he has a really good article on how circle-rectangle collision works, and you could even test it using this nice little graphic up here. I really recommend giving this a read, I think it explains things a lot better than I would be able to do. But the bonus of this website too is it gives you all kinds of collisions as well. So you can learn about like point, circle, circle, and so on and so forth. Again, this will be linked in the description if you want to learn some more advanced triangle collision stuff. But since I adapted my circle rectangle collision from their work, I'm just going to basically paste it in here. I have this function, circle rect. It is a worklet, and basically what it does is it checks if the distance in the rectangle itself is less than the radius. If that's the case, then we will return true. Okay, so at this point, we're going to make a function called check collision, and this is going to kind of behave as like a hub for all of our different collision checking on every frame. So let's call it check collision. And it's going to take in an O1, which is a shape interface, or object1. It's also going to take in an O2, which is a shape interface. And basically we're going to check if those objects have collided at all. So in our most basic case, we're just going to return false for this. So we're going to say collision info is going to be null, and collided is going to be false. However, we're going to do something a little different if the combination of things passed in is different. So if the first object getting passed in is of type circle, and the second object getting passed in is of type paddle, then we're going to do some collision checking. So we're going to get the x distance first, which is going to be the second object, the x value, minus the first object's x value, and the y distance, which is the second object's value, minus the first object's y value. And finally, we're going to do the total distance, which is also the Euclidean distance, which is math.square root. And we'll say math.pow. And the x distance to the power of 2 plus the y distance to the power of 2. And then finally what we're going to do is we're going to say that this first object is a circle, and the second is a rectangle. Sorry, a paddle. And we know this because we checked it above. And then we're going to check if it is a collision using our collision function above. So in here, we're going to pass the circle object's x value, the circle object's y value, the paddle object's x value, rectangle object's x value, and the rectangle object's y value, and finally the width of the paddle and the height of the paddle. And I actually have to call the function too, not circle object, it's called circle rect. Okay, and so next we're going to say if there is a collision, do is we're going to return a collision object with all the different things we need. So let me just copy this to make sure it's the same structure. We're going to say collided is true, and our collision info is going to have the first object, the second object, the x distance, and the y distance, as well as the Euclidean distance. Okay, so the next steps that we're going to have to take are first collecting all of our collisions. Then after that, we are going to resolve all of those collisions. So to collect them, we're just going to create an array. And it's going to be an array of type collision, which of course I have not made yet. So let's go and make that type now. So in our types file, we're going to make collision, which doesn't extend anything. It's going to have a shape interface for object 1, a shape interface for object 2, the x distance, which is a number, whoops, the y distance, which is also a number, and the total distance, which you guessed it, is of course a number. Okay, so back in our logic, we need to import that. And we're going to start this as an empty array. Next, what we're going to do is we're going to loop through all the different objects that we have, and we're simply going to just check if they collided. So we're going to say that we want to check for I and object 1 of all the different object entries. And then we're going to do the same thing. We're going to have like a double nested loop and get all the O2s. And inside of here, we're going to say if I is less than j, what we want to do is get our collision info for the two objects O1 and O2. And then what we're going to do is if it collided and there's collision info, which there really should always be if it collided, we're going to say collisions.push, and we're going to push the collision info right here. Okay, so now that we've collected all of our collisions, let's make another function that will resolve them for us. And we're going to resolve them in a pretty simple way. Oops, not resolve all collision, it's going to be resolve collision with bounce. And this is going to take in a collision info object. And then we're first going to cast our O1 to a circle interface, because we know it always is, after making it a worklet, of course. O1 as circle interface. Next thing we're going to do is take the circle info y value, and what we're going to do is we're going to subtract from that the radius. This is kind of like what we did before with wall collisions, almost exactly. So basically we're taking where we've impacted the paddle and we're subtracting the radius from that. The other thing that we're going to do is we're going to send the ball back in the other direction, and we already know how to do that from the wall collision. So we just take our Vx and we take our Vy and we make that equal to the negative version of the Vy. And then we do the same thing with the AY, we invert that as well. And that's going to get things bouncing in the opposite direction of the way that they came in originally. Okay, so we're almost ready to test this, but first we gotta finish a couple things off. Oops, that should be a worklet. That would have been bad, that would have crashed the app. But the last thing we're gonna do now that we have all of our collisions array, is we're going to loop through them and we're going to resolve them all using the bounce like we showed earlier. So we're going to say for collision of collisions, we are going to resolve collisions with bounce and pass our collision object in there. All right, so let's reload our app. Oops. Let's reload our app and see if it worked. And as you can see, the ball is bouncing off the paddle, really nice, like we like. And just to be super sure, yes, it'll bounce off the ground as well, which is good. So the game is actually detecting where the paddle is, and it's bouncing off either the floor or the paddle, depending on what the math says, which is great. Okay, so now that we have the paddle working, the next thing that we're going to do is start working on our bricks. And for our bricks, we're going to make an interface for that. And it's also a shape, so it's going to extend the shape interface. And inside here, the type always has to be brick, of course. And let me just add that to our types really quickly. Okay. A brick will also have a height and a width just like the paddle, but it does have one distinguishing factor, and it's this Boolean can collide. It needs to be a shared value because whether or not the actual brick that's displayed on the UI is visible and whether or not we need to be controlling for collisions on it is something that does need to be dynamic and does need to be controlled by the UI, so we do need to keep it inside of a shared value. Now that we have our model ready, what we have to do is actually draw the bricks on the UI, and that's going to take a little bit of effort. So let's first create a prop interface for the brick, and that's just going to include an index, which is going to be a number, and it's going to have all the data for the brick, which is going to be our brick interface. So we're going to say that our brick is going to be a component, and it's going to take in the index and the index and the brick from the props. Inside here, what we're going to do is we're going to change the color depending on how the can collide status changes that I showed you earlier. We have to use a derived value for this, and that value is going to change on the brick.canCollide. And what we're going to do is, based on the value of can collide, we're going to make the default color either orange or transparent. So basically, if you're not able to collide, the color is just going to be transparent and you're not going to be able to see the brick. Inside here, what we're going to do is we're going to make the brick a rounded rectangle. And just for fun, inside of here, I'm going to put a nice linear gradient. And I'm going to start the gradient at just kind of an arbitrary place and end it at a place that to me looked kind of nice. Should be 300. And I'm going to do the same thing with end. These are just arbitrary values. You can kind of make them whatever you want if you want to play with the gradient on your own. But basically the colors are going to go from red to orange. Okay, so let's set the values of the actual rounded rectangle. Its key is going to be equal to the index. The X position is going to be equal to the brick's X position. And you've already seen this pattern quite a bit already with these like interfaces that I've been making, but I'm gonna do it one more time here. The width is gonna be the brick's width. The height is gonna be the brick's height. The color is gonna be the color above, and the radius is gonna be equal to 8. Again, just because I thought that was a nice value, not for any real specific reason. So now let's actually draw those bricks on the screen, and this is going to be a pretty long function, but I'll try to do my best to explain as I go through. So we're going to create our bricks, which is going to be an array of type brick interface, and it's going to be like sort of a range-based for loop, I guess you could call it, but JavaScript doesn't really have one, so we create our own version of it by filling whatever we want the total bricks to be by 0, and then mapping over that. In here, we ignore the first value, but we do need the index, because the first value is always going to be 0, because we're just ignoring this fill here, right? So inside here, we need to say the x position of how far the farthest brick is, so the brick that's on the right-hand side. To do that, we're going to use the brick middle constant, and we're going to add the brick width to that. And then the last thing we're going to do is add 50, so we have a little bit of buffer between the bricks. The x position for the middle brick is just the brick middle constant. And then the close brick, which is the brick furthest to the left, is always going to be the brick middle minus the brick width minus 50. So just in case it wasn't clear, we're going to have 3 bricks on the screen at any given time. The one on the right is going to use this as its x value, the middle is going to use this, and the one on the left is going to use this. We're going to change the y values to be dynamic, but the way that the x works is basically the same in all cases. So to set the starting x position for any given index, we're going to check against the brick row length in the modulus. So if it's the first brick in the row, which is signified by the value 0, we're going to say that the starting x position is going to be equal to the far brick. We're then going to check, oops, this should be a modulus, not an and. We're going to do the same thing with 1. And if this happens for 1, the starting x position is going to be equal to the middle brick. And then we're going to do the same thing with 2. So the starting x position is then equal to the position of the close brick. So at this point, we've set all the x positions, or what they're going to be, and I'm able to rely on modulus because I want rows of 3 every single time, which is what we're getting here, and the x position is the same regardless of how deep you go with the y. So for the starting y position now, the way we're going to calculate this is we're going to get the starting y from a constant we're going to sort of make here. And that's just going to be 60. And then we're going to make a y spacing, which is the distance that we want on the y-axis between the rows. And we're going to say starting y plus the y spacing, and then we're going to multiply that by the floor value of the current index divided by the brick row length. Okay, so now that we have all these values, we're going to return a brick and that brick is going to have an ID of 0 because it's never going to change. The x value is going to be the starting x position, the y value is going to be the starting Y position. The AX is going to be 0 because it never moves. Same thing for the AY. Same thing for the VX and the VY. Now the height is going to be the brick height, which is also a constant I made earlier. The width is then going to be the brick width. And finally, can collide is going to be equal to a shared value of true, because when they're initialized, of course, you can always collide with a brick, and that's not a problem. Okay, so really quickly, let's actually fix this typo that I made here. Actually, it's a copy paste error. And now what we're gonna do is we're going to actually draw the bricks. So how we're gonna do that is just like any other component, we'll just do bricks.map. And inside here, I'm gonna take our brick and index, and then we're going to return our brick Skia component. And inside of here, the key is gonna be the index key. The index is gonna be the index. And finally, the brick is gonna be equal to the brick that we have in the loop. So let's reload and let's see if that worked. Cool, and so we have bricks. Obviously we can't collide with them or anything like that, but they are drawn. So let's work on the actual collision piece now. So now that we have our bricks drawn on the screen, we're gonna add them to our array of things that we can collide with. After that, we're gonna update our check collision function. Remember I said earlier, this is gonna be our hub for all the different types of collisions. And again, it's gonna be our hub here. So we're gonna copy paste this, but we're gonna say if a circle collides with a brick this time, we're gonna do some different things. So the first is gonna be if the second type is a brick, what we're gonna do is we're gonna cast the object to a brick. Then we're gonna check if the brick is in the can collide state. And if it's not in the can collide state, we're just gonna return a non-collision like we had down here, because the brick is technically invisible at this point, so you have no way of actually colliding with it. So now if there is a collision, we are gonna treat things slightly differently. So we're gonna say if the O2 type is a brick, we're gonna again cast to a brick. But this time what we're gonna do is we're gonna say the brick dot can collide value is now equal to false, which should make it so that you can no longer collide with it. All right, so let's run this now and see if we had any luck. And ball's coming in, bang. And as you can see, we can now collide with the bricks, which is really cool. All right guys, so we're coming up on an hour now, and I don't want to make this video too long, so I'm gonna leave the last bit of ending the game as a homework for you guys. It's not a hard thing to do though. Basically what you would do is you'd pass in the brick count as a shared value into your animate function. After that, in your wall collision, what you would do is once you hit the bottom, you would then set that value to -1, and when it was -1, you would show the end screen. The next thing that you would do is in your animate, if you resolved a collision with bounce, you would increment this by 1 every single time there was a collision with bounce. And when you finally hit the total number of bricks that you needed to hit, you would then end the game with a you win screen or something like that. Okay, so last thing that we're gonna do is we're going to grab the use clock from React Native Skia, and down near the bottom here, we're gonna create some uniforms, which are values that we pass into a shader. It'll have the dependencies of width, height, and the clock. And the resolution is going to be equal to a vec with the width and height. And the time is going to be equal to the clock value times a very, very small number so that I can slow the shader down to a reasonable value. The other thing that I'm going to do is I'm going to make a rectangle that's the exact same size as the canvas. And inside of there, I'm just going to throw my shader in it. Okay, so let's see what this looks like. And as you can see, we have a beautiful shader along with our app, and we can do all of our collisions extremely nicely. So that's everything, guys. I hope you'll do the homework. I hope you enjoyed this. And yeah, happy hacking.